We're going to start off today with domain and range, finding them graphically. If you were to sketch the graph of y equals the square root of x, the first thing you would do is make a table of values. So in your table of values, the square root of 0 is 0, the square root of 1 is 1, and the square root of 4 is 2. So for your graph, you're going to select points at 0, 0, 1, 1, and 4, 2. This graph looks like half a parabola. When you're answering questions about domain, you're looking from left to right because domain is x values and x values go from left to right. This graph starts at 0, that's the lowest point, and it goes on forever, so it goes to infinity. Therefore the domain is 0 to infinity. If I look at the same graph, but this time I'm looking at range, range is the y values, and so you can think of range as going from the lowest point to the highest point. And for this same graph, the lowest point on the graph is here at 0. And this graph, even though it sort of looks flat, it does keep going up forever because the bigger number you square root, the bigger answer you'll get. So the range starts at 0 and also goes to infinity. Now you can also find domain and range algebraically. You can also find the domain and range algebraically. To find the domain algebraically, you're really just looking for things that you can't have. Like in this example, you can't have x is equal to 0 because you can't have 0 on the bottom of a fraction. So this domain would have no values of x at 0. And if you were looking at that in interval notation, it would be from negative infinity to 0, union 0 to infinity. There's other types of problems for domain, like if I look at the problem above, let's say one similar to that, like y equals the square root of x minus 4. In this case, x minus 4 would have to be greater than or equal to 0 because you can't take the square root of a negative. And if I were to solve that, x would have to be greater than or equal to 4. So algebraically, for this blue function, the domain would start at 4 and go to infinity. Most of the time, it's just easier to find the range graphically than algebraically, but the method for finding the range algebraically is to switch x and y, solve for y, and then give the domain of this inverse function, and the inverse function, what you got when you solve for x and y, the inverse function's domain is the algebraic range. Today you will also have to identify if a relation is a function, and I'd like to give two examples that are easy to think about. I'm going to take student 1, student 2, and student 3 and ask them their age. Student 1 says, I'm 15. Student 2 says, I'm 17. Student 3 says, I'm 17. This is a function because each student has exactly one answer. It doesn't matter that both of their answers happen to be 17, that could happen. The important part is each x value has exactly one answer for y. If I were to ask student 1, how old are you? And they say 15. And they're like, oh, nope, I meant that I was 16. And they're like, oh, wait, I need to get in to this dance. I'm 18. You can't have one student give 3 different answers for their age. This is not a function. You can also tell if a graph is a function by looking at the x value and looking to where the corresponding dot on the graph is. This only has one spot on the graph that corresponds to the x value, so it is a function. Whereas for the circle, if I'm looking at this x value right here, it has a corresponding y value both above and below it. Since there are 2 corresponding y values, this is not a function. And this method is sometimes called the vertical line test. If I look at a vertical line right here, it only touches the graph in one spot. If I look at a vertical line right here, it touches the graph in two spots. Two answers is not a function. Let's take a couple more looks at domain and range before we skip to the next thing. Let's say we had the graph y equals 4 minus x squared. This graph is a parabola. It has a vertex at 4. It's upside down. If I'm traveling along this parabola from left to right this way, then the domain is all real numbers, which we write as negative infinity to infinity in pre-calculus. Now, it might look like it goes down, but really it is getting wider the whole time, because the bigger number we put in for x, the lower y is going to get. And you can put any number in for x, so x can go on forever. But if I'm looking at the same graph for range, I'm looking from bottom up to the top, and this graph stops right here at 4. Now it goes down forever, but it stops up at 4. So the range for this function is going to be from negative infinity up to 4. Now in this section, you're going to be expected to graph lines, which we did in the P chapter. You're going to be expected to graph parabolas, which we also did in the P chapter. You're going to be expected to graph absolute values, which we're going to actually review tomorrow. And you're going to be expected to graph rational functions, which is the next thing we're going to review in this video. Okay, you're going to have to know basic graphs. You're going to know the first graph is a line, and if you were to graph that line, you would go up 3, and after going up 3, you would go up 1 and over 2, sketch the function. You'll have to know that the next squared graph is a parabola. This has a vertex that's shifted down 4, and this parabola faces up. You'll have to know that a square root graph kind of looks like a sideways parabola, except for when you do the square root graph, you're going to have to make a table of values and make sure that you have no negative numbers in your table. So like for this graph, I would say that the square root of 0 is 0, and the square root of 1 is 1, and the square root of 4 is 2 for my x and y values. And when I sketch that graph, compare it to the parabola, it looks like half a parabola without the negative signs. Absolute value graphs are V-shaped. This absolute value graph is shifted to the right 5, and it has a slope of 1, and it sort of gets ricocheted off the vertex and goes back at a slope of -1. These graphs are all going to be pretty easy. The hard part is going to be graphing the rational functions, which we'll take a look at below. But without the interval notation, on this first graph, the domain and range are both going to be all real numbers. The second graph, the domain is going to be all real numbers, but the range is going to start at -4 and go to infinity. On this third graph, the domain and range are both all numbers greater than or equal to 0. And on the last graph, the domain is all real numbers, and the range is going from bottom to top. It starts at 0 and goes up to infinity. Now, on your homework assignment, that needs to be an interval notation, but this gives you kind of a basic idea. So the hard part of the homework is that most of the graphs you have to give domain and range for are rational functions, and they're more difficult to graph. So for graphing rational functions, you're going to identify the vertical asymptotes. To identify the vertical asymptotes, you're going to look at what makes the bottom equal to 0. After you find the vertical asymptotes, you're going to identify horizontal asymptotes. If, like this problem A, the bottom power is bigger, then the horizontal asymptote is at y equals 0. So you're looking at the powers here. This has a power of 2. This has a power of 4. The bottom power is bigger, so the horizontal asymptote is at 0. in problem B, the powers are the same. You have an x to the 1, you have a 3x to the 1. And so when the powers are the same, you look at the leading coefficient. This would have a horizontal asymptote at y equals 1/3. In the next example, the top power is bigger. When the top power is bigger, there's no horizontal asymptote. You have to do long division, and in this case, the x minus 2's cancel, and you end up with x plus 2, which is a line, but this line has a hole at 2. This next example also has the top power is bigger because we've got a power of 2 here and we've got a power of 1 below. But in this case, it doesn't cancel out nicely, and so for these problems, you're going to have to do long or synthetic division, and this is going to have no horizontal asymptote, but because it didn't divide in evenly, that means it's going to have right here at x minus 1 a slant asymptote. Now, I only have 2 minutes left to keep this video small to get on YouTube, so we'll look at more examples of rational functions in domain and range, but if you need further examples, take a look at Mrs. Search's video. Okay, so now let's look at a full example of graphing a rational function, and we're going to start off with y is equal to 1 over, let's do 2 minus x. So, first thing I do is I look at the bottom of the function. Whatever makes the bottom equal to 0 is what you can't have. You can't have the bottom equal to 0, and that will be the vertical asymptote. So, since 2 minus x cannot be equal to 0, if we solve that, we end up with x cannot be equal to 2, and so this graph has a vertical asymptote at 2. Second thing we look at is the powers. This graph has an x to the power 1 on the bottom, but it has no x's at all on the top, so therefore the bottom power is bigger, so the horizontal asymptote is at 0. After identifying the asymptotes, we test points. We test points to the left and to the right of the vertical asymptote. I'm going to test the point 0. At 0 I have a value of 1/2. I'm also going to test the point 3. At 3 I have a value of -1/2. So this graph has a point here and here, and because the asymptotes act like force fields, the graph is trapped between the two. This rational function has a domain from -infinity to 2 and from 2 to infinity. This rational function has a range from -infinity to 0 and from 0 to infinity. Remember, your goal for the homework assignment is to give the domain and range, but you're giving the domain and range on problems that are kind of tricky to graph, and part of the assignment is also making the graphs. Okay, I am calling it quits because this program has crashed 3 times now, so if you need more examples, check out Mrs. Search's video. Homework assignment will be online.